Okay, I'm going to start this talk off the way that I wish many more talks started off with, and that's with a theme song. So if you'll indulge me, let's hit it. I don't want to interrupt the funk, we got a lot to cover. This song is called Amen, Brother. It came out in 1969 by a band called the Winstons. It was the B-side. Can you guys? I should be near the mic. There we are. It came out in 1969 by a band called the Winstons. It was the B-side to a song called Color Me Father. Color Me Father ended up going on to some success. It won the composer a Grammy, hit number 2 in the charts. But like a lot of B-sides, Amen, Brother was largely forgotten. And it went that way for a number of years until a part of it that was discovered that's sort of gone on to an absolutely infamous, to have an infamous reputation. And that's a little otherwise incidental 6-second drum break in the middle of this song. So let's hear it. Not much, right? 6 seconds, 4 measures, but it's 4 measures that have gone on to inspire and to build entire genres of music. We're here almost 50 years after this song came out, and new songs are still being made based on this. It's called the Omen Break, and it's been sampled a known 2,300 times, countless times more by amateur and bedroom musicians the world over. Jay-Z has sampled this. It's in the Futurama theme. It's everywhere. And I think that's really cool, right? That this bit of music from 40 years ago, that 50 years ago almost, that no one at the time had any, idea that it would, have any life to it, has sort of gone on to not only stand the test of time, but to still be inspiring people today. I think that's really cool. And I think it's also really cool because we are actually going to play that today in Elixir. And we're going to do, as Brooklyn so eloquently said in her first talk this morning, rather than solving the specific case, we're actually going to do something a bit more general than this, and we're going to build a drum machine. So there's a ridiculous amount to cover in this talk. I'm just going to jump right into it. There's basically 4 parts, 4 things I want to talk about. The first is I'm going to introduce some scheduling patterns that underlie this. The second part is I'm going to talk about SCEDX, which is the library that we use in production worldwide to power dozens of factories, thousands of events a day, called SCEDX. And we use SCEDX in this talk to actually go and build the drum machine. So the third thing we're going to do is actually demo the drum machine. We call it beats. And for the fourth thing we're going to do is we're going to take beats and we're going to use that to build some beats, specifically the Omen Break. So I really hope we manage to get there. Can I see my time? Yeah. I really hope we're going to be able to get there. So let's move along. First up, scheduling patterns. So I can't think of a better way to talk about this than to talk about where SCEDX, the library, came from. So in my day job, I'm an independent software consultant in Toronto. My current gig is with a company called Funnel Cloud, and they build what's called a manufacturing execution system. Now, that's essentially a piece of software that runs a factory, and is the short way to say it. It does things like managing shifts, managing breaks, tracking production, machine state, running reports for management, that sort of thing. But the really important part that I want to talk about today is scheduling. So just to give you guys a quick, really high-level overview of it, this is what's called a plan actual report. This is a report that is essentially a time strip for a given machine in the factory, and it shows what portion of the time it was running, which portion it was down, when it was idle. So the idle ones are those amber ones at the bottom. You'll notice the one that's highlighted there goes from 9:30 to 9:45. That's a break, and that needs to happen exactly at 9:30 every time that it's scheduled to happen, and it needs to end exactly at 9:45. Right? These are factories that cost tens of thousands of dollars a minute to run, and this kind of precision is par for the course in this world. Another view is, for a variety of reasons that I won't get into, we run our own internal escalation system, much like PagerDuty. This is all backed by SCEDX schedules as well, so when an incident fires, we schedule timers, in this case, for 30, 60, and 120 minutes out. When those timers fire, jobs get dispatched that go and notify the relevant user via the relevant channel. Third example is this beautiful creature here. This is called an andon board. If you ever walk a factory floor, you'll see one of these next to just about every machine. It calls out a bunch of numbers that aren't at all important to understand, that are critical to the people running the machine. You'll notice on the left-hand side there are 9 timers. Those all eventually resolve back to SCEDEX instances on the back end. So all of this is really just to demo that there's timers everywhere in this domain. And we quickly found that these, as you would expect, get factored into a common library. We took that library and released it out, and we call it SCEDEX. There's stickers of this logo at the end of the talk, by the way. So if anybody wants one, I've got a pile of them. Whoa, a pile of them here. And our goal with this is to really build something that's an analog to like Gen server OTP levels of reusability, but with scheduling and with time. And there's really 2 aspects of time that I want to talk about just to demo. The first is timers that are sort of relative to some given interval, usually now. So do something in 30 seconds or in 30 minutes or whenever. The SCEDEX, the way you do this in SCEDEX is you call SCEDEX.runIn, give it a module function argument. There's a functional method to this as well, and a 30,000 that's just 30,000 milliseconds. It gives you back your standard OK PID tuple, and 30 seconds later that MFA fires, and in this case, hello world gets output to the console. Another example these are a bit more interesting and much more sort of germane to the domain that we work in, and these are events that are recurrences. And I thought Wojtek's talk this morning was really fascinating for this because we took a different tack with this, which is to use cron tabs for this. Over here on the right-hand side, I don't know if this side of the room may not be able to see it, but it's the exact same call, module function argument, except the fourth argument is a cron tab string. And you can use this. If you've never read a cron tab before, this one essentially says it's minute, hour, day of the month, month of the year, day of the week. So this says at 10:30 every morning on the 1st through the 5th days of the week, fire this cron tab. So you run this, you sit around in your console, wait till 10:30 the next weekday, and you're off to the races. So those pieces are both pretty straightforward. They almost seem trivially simple, and they really are. That's by design. Where I think SCEDEX becomes really powerful is when you start thinking of it in terms of composing it with the rest of OTP. So specifically, one of the things that we really drive towards with this is that it's supervisor friendly. So those calls return standard OK PID tuples, which means that you can wire this up in your application.ex file if you wanted, let's say, cache bust every 5 minutes. You can just have a line in your application.ex file with a SCEDEX call that can call directly to your cache busting method, and your application just takes care of supervising that for you. There's no supervision intrinsic in SCEDEX. It just leans on the rest of supervision in OTP. Similarly, we can do this. We had a great talk at the speakers dinner last night about some of the things that are easy in Elixir but impossible otherwise. Or impossible in the Rails world, which is where we came from initially, as many of us have. And that's specifically with the ability to be able to schedule those, like I showed you earlier on the plant actual reports, the lunch breaks. So there's an interface where the plant manager can specify those. We have a back-end system that essentially just rips over those entries in the database, fires up a SCEDEX value, starts it up, gets an OK PID back, and hands it over to a dynamic supervisor. So no supervision at all internally. We lean on all of the supervision inside OTP to do that, and it works a treat. Like, you can do fantastically complicated scheduling bits with like 30 lines of code. We support time zones in DST. I'm not going to say much about this except to say that everything you know about time doesn't convey nearly as hard as this stuff is. It's absolutely diabolical, the number of corner cases, especially around daylight savings. SCEDEX goes to great lengths to insulate you from that as much as possible, so you can schedule against time zones. You don't have to worry about scheduling things over DST transitions. SCEDEX just manages it. It has this really awesome feature called timescales, which is actually underpins the majority of the rest of the talk, so I'm just going to let that hang for a second, and some other features that I'm just going to skip in the interest of time here. So timescales are something I just want to talk about briefly. They were born out of a need to be able to write testable code, and one of the things that we drive towards in testing, of course, is strong parity between what you're testing and what you're running in production. And that's really difficult, especially with time-based stuff, because you don't want to have if you have a job that, let's say, runs something at 10:30 every weekday, you can't have your tests wait around until 10:30 the next weekday to verify that whatever that thing is took place. So we have this idea of what we call timescales, which essentially let you accelerate time inside SCEDEX. So in this case, the SCEDEX.runEveryCall is the exact same as we saw before, except there's this extra argument for timescale. And the timescale is just a module that exposes a few methods. SCEDX consults this when it does all of its scheduling internally. And so in this case, there's an extra tick there. There shouldn't be. That's a typo. In this case, it essentially just accelerates time 86,400 times. So you can run this. You sleep 1,000, so you sleep for a millisecond, for 1 second, and SCEDX internally has run an entire minute of time in that interval. So you can verify that whatever side effects you expected to have happen within the next 24 hours have happened. And SCEDX, when it plumbs all those times through, gives you the correct time. So you get back timestamps to be what you would expect. This has tremendous benefits for tests because all of a sudden you can justify waiting a second, right, in these particular narrow test cases to be able to verify that your cron tabs are correct, for example, or that like the SCEDX itself is actually working. So this is actually this is really the core conceit that powers a lot of beats, the drum machine, and that's really where the rest of the talk's going to be. So there's exhaustive examples of all of this on the README for SCEDX. So I urge you, if you have any scheduling needs at all, please take a look at SCEDX and let us know, give us feedback on this. We'd love to hear of success stories with it. We use it in several dozen factories around the world. It's been running flawlessly for almost 6 months now. We like it a lot. I think you will too. So let's turn to the exciting part of this talk now, namely drum machines. So Beats really came from an internal need that we had at Funnel Cloud to sort of assess what the runtime characteristics were of Elixir in general and SCEDX in particular when we started running things on tighter loops. So we are starting to have customers demand features in Funnel Cloud that sort of feed back into process control on the factory floor. And these are things that have some like sub-second performance requirements. We need to have fairly strong guarantees on what those mean and on what those values are. And so we started off exploring this, and the idea was initially that we were going to build a machine that went bing, right, in the Monty Python sense. So we built the SCEDX, and it actually just played bing, 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 and then we went and did a bunch of other stuff on the machine, and the idea was if we were putting too much load on it, you would hear irregularities in the bing, right? And one thing led to another, and the next thing you know, we built a drum machine out of it. So, right? Necessity is the mother of invention, right? So anyway, that's generally the idea. And I don't know, has anyone here actually done, not that I can see anybody, but has anyone actually done any electronic music production or used the drum machine? Okay, so at least you, and probably a number of other people here, will recognize this app as being Ableton, right? This is largely the de facto standard for live music performance these days, at least electronic music performance. So Ableton internally has a sequencer built in, so it does all of this work. But certainly for our needs, that's not enough because we have to build it ourselves, but also for people that are using this for performance, it's not terribly tactile, right? You're not, as much as you often see people hunched over laptops, on stage these days, ultimately what you really need as a musician is something that's more tactile, right? And so what people start doing very quickly with this is adding on hardware to control devices. These are called control surfaces. And essentially what this does, it does a number of other things, but for our purposes, you can think of this grid of buttons here. They're LEDs, so you tap them and the light turns on. The columns are notes, are beats within a musical measure, and the rows are instruments, right? And so if you tap this guy and that light turns on, and you hit play, and the music sort of sequences through those columns, if that light's turned on, the corresponding sound plays when you go past it. So just as a bit of a digression here, I think I'm doing okay for time, so we're okay for this. If you start tracing the history of this back and you start trying to understand where this came from, because I think it's really instructive to know where, why these idioms developed the way they did, and you start looking at the history of drum machines, you very quickly come up against this guy. So this is the Roland TR-808, released in 1980. This thing is, it's impossible to overstate how influential this device has been on the history of modern music. Entire genres of music would not exist today were it not for this device. It definitely wasn't the first drum machine to be made available to the public, but it certainly was the most influential. The interface is very idiosyncratic. It's an analog synthesis device, so most of the actual electronics inside are analog. The interface for the top half of it is extremely idiosyncratic. It's not at all important to understand that. The part that I want to focus on is this bit here. So there's 16 buttons across. Each of the buttons has a little LED inside of it. And you can essentially think of this as one row in that step sequencer previously. So if you hit the button 7, let's say the 7th LED turns on. When you hit play, the music progresses through that, and the instrument that you're editing at that point then plays when the beat hits the 7th beat. So this is really interesting because this was really the first device that really presented this as a creative canvas, first and foremost. The device that came before it was a much less influential CompuRhythm CR78. And this was a device, the product brief for this originally pitched it as an accompaniment tool for home organists, right? And really, at first glance, it looks very similar, right? It's got some knobs, some buttons, some dials, and a row of buttons on the bottom. But if you zoom in, you see that these don't correspond to numbers, right? These are genres of music. So if you want to be accompanied by a rock beat, you hit rock. If you want to be accompanied by a bossa nova, you hit bossa nova. Like, I don't know why you'd want to do that, but you can, right? Anyway, so people being creative as they are, figured out ways to hack this thing somewhat to sort of change it a little bit. But there ultimately wasn't a whole lot of, it wasn't a tool for creation first and foremost. It was a tool for accompaniment. And so when you go back and look at the 808, you can see how this is really a blank canvas, right? When you turn it on, it doesn't do anything. There's no button you hit to get a rock beat, right? Or to get a two-step. You really, if you want something, you have to build it yourself, right? And that DIY ethic really sort of shaped the future of the interface for drum machines. So the 808 was followed a few years later by the 909. Very similar UI in terms of how the buttons are structured. The key difference here being in terms of the sound, the 909 was sample-based, at least partially, ended up having a harder, punchier sound, where the 808 was instrumental in the development of hip-hop. The 909 was really instrumental in house music and techno music just because of its harder sound. But fundamentally, the user interface was largely unchanged between the two. A few years later, the 707 came out. Again, very evolutionary as opposed to revolutionary. The thing that makes the 707 interesting for our talk, though, is the fact that it has this little display. And what this really does is unwrap all of those rows for each of the instruments and display them in one sort of consolidated grid. And so you can start seeing now how this looks like the control surface that we saw a few moments ago, right? Instead of light up LEDs, there are dots on here, but the pattern's there. And I think that if anyone here is trained in instruments other than, or has not done any electronic music production, if you know how to play an instrument and you sort of look at this and squint your eyes the right way, it does sort of look a bit like sheet music. Right, and so as an example of how to go to that to the drum machine pattern from sheet music, we'll look at this. So this is a standard rock beat. The X's on the top are your hi-hat or your cymbal. The eighth notes on the bottom are bass drum, and the quarter notes are snare. Right. So if you listen to this, it might sound something like boom boom ch, boom boom ch, boom boom ch. Right. Not terribly interesting musically, but it serves to illustrate. If you think about how you might translate this into a grid of buttons, it might look something like this, right? So again, the top row, snare drum, middle row, top row hi-hat, middle row snare drum, bottom row bass. And when you hit play on this, the lights go across and the instruments play as you'd expect. So it would sound something like boom, boom, ch, boom, boom, ch, right? So that's really the sort of the 30-second or 2-minute review of sort of the history of the idiom so that we can understand what Beats looks like and why it looks that way. So let's take a look. So Beats is a standard Elixir app. Nothing terribly surprising here. It runs, why don't I have this in my history? There it is. It runs as a command line app, largely just for the retro stylings of this. I'm really a sucker for this. This uses end curses. So Frank Huntleth is in the audience somewhere here. I don't know where he is. Huge shout out to him for updating this library. Thanks. Yeah, I couldn't pass up the retroness of this. Also, I've never written a line of Phoenix in my life, so I wouldn't even know how to start on the web. But generally, you can see what this looks like, right? You've got the rows, they've got the columns. And when you hit play on this, I really hope the AV setup works. OK, it doesn't. Hold on. So Ableton does this thing sometimes where you need to kick it in the pants to tell it to work. Right? So you can sort of see how this works. I'm going to turn this down a bit so I can speak over it. Right? So the lights go across as the relevant note hits, the relevant sound fires. You can control the tempo of this, so you've got keyboards interface into it. Again, necessity being the mother of invention, I developed this little control knob. So this has a, right? And it speeds it up. This is also driven by MIDI, right? This is just using MIDI that gets tunneled into beats instead of into Ableton. You can slow it down, right? Pretty cool. In terms of the interface to be able to make the sounds out of this, it's driven by files. What are we doing for time? Good. Okay. So essentially, each of these songs is you know what? I'm going to switch these because this is. Move this up here. Where was I? No, come on, up here. There. Just so everybody can see that. So generally, the idea here is that each of the sounds corresponds to a row here. This is just a JSON file. So you can live change this, and let's say do this. And when you save the file, Beats has a file watcher, so it reloads the file the next measure around so that you don't sort of break, it doesn't break your rhythm. So, right, you can do that. You can change this guy. Whoops, whoa, what did I do? Hold on. You can add little emphasis in here. Oh, shoot. Sorry, it's actually, Vim is really not built for live editing, like, especially when you've got nerves, right? Right, you can add some, let's add some hand claps in just to make this sound really 80s, right? Right? So that's kind of fun. And the cool thing is it's all file-based, right? So if you don't like what you're doing, you can just undo it all, go back to this, hit save, right? So it's cool because your music lives in source control, which is actually pretty rad. If you actually go and look at the history, the Beats program, I'll have the link for it at the end of the talk. Let me just stop this so I'm not speaking over this. Oops. Yeah, you can see in the source repo for Beats, there's like, you can see all the changes to these as I'm developing, so you can see all the musical mistakes I've made, for better or for worse. So let's take a look at how this actually works under the hood. So again, standard Elixir app. So Beats is the bit inside that sort of rectangle in the middle. There's a bunch of other modules that aren't on here. There's stuff to run the display, stuff to interface with this knob, a bunch of some stats modules, nothing terribly important for the talk. This really illustrates the flow between SCEDX, running Beats, passing them into a metronome module that turns that into something that in the musical domain passes metronome notes over to a conductor who goes, consults a score, takes all the notes that are supposed to fire for that, maps over them, and emits them over MIDI out to Ableton. So it's a pretty sort of straightforward flow. Once a tick comes in from SCEDX, it fires all the way through that. What I want to talk about, though, briefly, is how this actually, how we use this structure and timescales, which I spoke about earlier, and how we use these to facilitate being able to change the tempo. So the initial flow of this, let's start with a 120 BPM example. So SCEDX, when it starts playing a song, says SCEDX.run in, call metronome.doTick every one. I'm not going to say what one is yet, just every one. And use this tempo agent guy as your timescale. So SCEDX says, great. Turns around, immediately asks the tempo agent for how fast the speed up should be. So we're kind of turning that speed up and test thing on its head, and we're using this to slow time down. And so we do that by returning a value less than 1. And in this case, we do the math and figure out for 120 BPM, that means that every 16th note is 1/125th of a second, is 125 milliseconds. So we return 1/125. And keep in mind that we told SCEDX to run every 1, right? So if you do the math, the 125 moves on the top, and SCEDX waits 125 milliseconds, and then calls doTick, right? From here, it's not terribly surprising. That gets forwarded through conductor into Ableton. It fires off the first beat. Immediately, SCEDX turns around, asks it again. We're still running at 120, so we return 1/125th. 125 milliseconds later, call comes in, displays the second beat, and this goes on and on and on every time you pass the 16th note. Then a message comes into the metronome that can either come from the UI module or from this guy. And he says, set the BPM to 121. So the metronome says, great, passes that down to the tempo agent. And then the next time SCEDX asks, the tempo agent does its math and figures out that, oh, OK, a 16th is now 123.96 milliseconds. So it returns that. The best we can do is 124 with that. I'll speak about that in a moment. So 124 milliseconds later, a tick comes in. And all of a sudden, now we're running at something closer to 121 BPM. And now the same loop repeats again, right? 124 milliseconds instead of 125. So the cool thing about this is that SCEDX doesn't actually change. We don't have to start and stop SCEDX. We just change the value that the timescale returns to it in a dynamic way. And then that allows you to manipulate the value of the BPM dynamically without having to restart or do anything with SCEDX. You never even explicitly tell SCEDX that the BPM's changed at all. It just does it implicitly by the tempo agent reflecting different delays. So there's a couple errors that come out of that. The first was that difference between 123 and 123.96 and 124. So this is pretty straightforward error, right? 120 BPM works out to 125.0 milliseconds. That's an integer, so we're cool, right? We were able to run 125 milliseconds on our ticks. So we actually realized 120 BPM out of the speaker. I mean, setting aside all the other errors, we realized 120 BPM. In the case of 121, the best we can do is 123.96, right? So if you work that out, the best we can pass in, because you're bounded by what you can pass into the Erlang runtime, which to pass in integer milliseconds. So we round this to the closest integer millisecond. You do the math backwards from that, and that turns out resolving to 120.96 BPM, not 121 that you asked for. So there's a small error there, but especially as the BPM start getting higher and higher, that proportion gets to be larger and larger out of the overall BPM. So that becomes, these sometimes hit the double digits depending on the values that you get further on. We'll see that in a moment. So the second type of error I want to speak about is this notion of what we call quantization error. Now this is really that same sort of idea of being constrained to have millisecond level precision when you call into the runtime, except this is internal in SCEDX. So where the rounding error that I spoke about previously is very particular to a drum machine. It's because we define ourselves in terms of beats per minute and then have to resolve that down to milliseconds. That's where the problem lies. In the case of if you were building something that was in a domain where you just said run it every 10 milliseconds, that you would implicitly have a 0% error because you'd be your entire domain would be built around integer milliseconds. Internally, however, SCEDX it always sort of ends up being called a little bit after the fact because it calls after the function call returns. And so it doesn't have the luxury of being scheduled exactly on a millisecond. It knows exactly when it needs to be scheduled for the next one, but it's only able to realize that at a scheduling level to the closest milli, right? So in this case, SCEDX would realize that I need to call myself 9.7 milliseconds in the future, but the best I can do is 10. So we can quantify that completely inside SCEDX, but we can't actually do anything about it. Well, we can't do anything about it unless we go and plumb microsecond granularity into the Erlang runtime. That's going to be my next talk. So it'll take me a while to do that because it's actually like there's going to be an Erlang enhancement proposal because it's a breaking change to the API. But and there's a few people in the audience that I really want to talk to about that later. Hopefully you know who you are. So yeah, that's going to be a good talk this afternoon. So anyway, that's the way to solve this, is to essentially expose microsecond granularity so that you have that flexibility when you schedule. The third is something that we talked about previously, that a few people have talked about already today, and this is garden variety, scheduling delay. You tell the computer to run something at 1030.00000, right? This is Wojtek talked about this morning in terms of the fantastic, how fantastic it is that we have micro precision on these things. And SCEDX will come back and say, I ran it at 0.0001, right? So it's a millisecond late, but that's 1,000 microseconds, right? That's a big number, right? And it's, there's nothing you can do about it. You're stuck unless you get a faster computer or just do less. But, it's definitely something to want to quantify as well. So speaking of quantifying, let's actually go back into beats and see what these look like. So I'm going to move this guy. Let me find my mouse here. Where the heck am I? No, seriously, where am I? There I am, okay. Let me just move this guy back on top here so you can see it. So we're going to start this guy again. I'm just going to bring the sound down because it's not terribly interesting. And let's speed him up. So we're currently running at 130 BPM. Let's go up, right, past the upper limit of what you'd ever, aside from some really frenetic rave scene that I've never heard about, right? And we can get pretty insane here. We're up at, I don't know if you guys can read this in the upper left corner. We're at 1,300, turn this down, 1,374, right? And you can keep going with this. You can get it up to, I've had this up to about 3,000 before, and it seems just fine. So you can see in the upper left corner, the rounding error is now at 2%, right? Because we're going faster and faster and faster. The ability to schedule to the closest millisecond, that millisecond error becomes a larger and larger part of it. But the interesting part from a stats perspective is this oh so pretty histogram here on the right-hand side. So this right now is measuring the dispatch delay, right? So the difference between when you tell the machine to run and when it actually runs. So in this case, this is a histogram that runs from 0 micros to 1,500, so from 0 to 1.5 milliseconds. And you can see that it's pretty stable, right? It seems to be hanging out somewhere around 600 microseconds or so a little more than half a millisecond of scheduling delay. And this is running, like, here, I'll just turn it up so you can hear, right? It's far faster than you'd ever need a drum machine to go. But it seems to be, keeping up quite well. And if we switch those stats over to be quantization error, you see these hang out around 300 or so, and those seem pretty stable, right? And if we sort of bring the beat back down to something a bit more reasonable, right? This is kind of neat too. I like this because as you're coming down, right, you can start. It actually starts resembling music right about here, right? And the cool thing is we didn't drop any beats. That's a continuum, right? Like, it's not like we stopped doing things. We were just playing them so fast that it just sounded like white noise. And that sort of comes back into something that we might recognize. And you can look at the numbers now. The errors seem to be very similar. Quantization still around 400 or so roughly about the same. Dispatch delay is still around 600 or so. So really, whether you're asking Erlang to run something at 150 BPM or 3,000 BPM, it's able to keep up just fine, which I think is a real testament to how awesome Ertz really is with this kind of stuff. So that's kind of the extent of what I wanted to talk about in terms of the mechanics of the drum machine. Let me just actually consult my notes here because I've got to go back to a few live demos now. And we're going to talk really briefly about some of the stuff that we can do with some actual beats coming out of this. So now we're in the fourth part of the talk. So one of the things that I really want to sort of emphasize here is that electronic music doesn't always have to be electronic, right? I can load up another song here. Any Zeppelin fans in the room will probably recognize this straight away, right? But this is a much slower beat. It doesn't sound rock. It doesn't sound, electronic at all. I mean, this song, make no mistake, this has been sampled up and down hip hop, right? So this is not, it's not like this doesn't have an outsized influence in modern electronic music, but fundamentally it's a Zeppelin song, right? So it's all about the rock. And you've got, the other thing I want to point out here is the fact that we've got this thing that we call fills, and these are essentially accents that get triggered when you hit the buttons on here. So I can go, right? Those are going to feature into the Omen Break in a bit. I just wanted to point them out. The other thing, what is going on here? Why is this? Oh, because I slowed it down. Right, okay, here we are. The other thing I want to point out here too is this notion of what we call swing, right? So if anyone's ever played any jazz music or done anything where you don't play a straight beat, right? The important thing to listen to here is how straight this sounds, right? It's like boom, 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 right? You can add a swing into beats that essentially starts emphasizing every other 16th note. And this starts sounding, for lack of a better term, jazzier, right? You can hear that, the bass drum, right? Boom, 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 right? It's more of a sort of a swung, lazier, more organic sounding beat. And you can bring it back, and it sounds straight again, right? And I think that's really cool because Elixir is able to tell the difference between those, which I think is awesome, right? The fact that you can have something that's accurate, that can schedule stuff accurately enough to actually play different genres of music using the same score, which I think is really, really, really cool. So anyway, that's it for sort of net new features. We're going to move on to just a couple of demos here. I'm actually doing really well on time, which is funny because in my dry runs, I was never able to get this talk done on time, but it seems like I'm actually pretty ahead of the game here. So it's the fear of God from over here, right? So we've got time for a couple other demos here. So I'm going to go back to the default song, the one we started off with, right? So this sounds pretty boring now that we've, right? I'm going to bring this up. I'm going to beat match it to 180, right? 178, I guess, is the best I can do. And I just want to talk briefly about the Ableton side of this, right? So we talked about how this is the drum machine. This just sequences MIDI notes, right? It doesn't actually play WAV files directly. It plays over in Ableton, right? And Ableton's got a bunch of whiz-bang controls. I don't know how to use any of this, but it's got a bunch of whiz-bang controls to throw things through reverb and a billion other things. But a friend of mine who knows a lot more about this set up a couple of different sort of drum kits in here. And in our scores, we have the ability to, right? I'm going to turn this down again. I'm just going to show you this two-step file. We have the ability to be able to set this channel here, right here, down in the lower file. So this basically says whenever you load this, play a separate channel in Ableton so that you get a different set of sounds. And so what you end up with is I'm going to switch between this beat and an identical two-step that just has a different set of sounds in Ableton. Right? And I'm going to do that by saving the file. Right? Other than the fact that it's just louder, right? It just sounds a lot punchier, right? And that's just really the difference in sounds that are coming out of it. It's the same underlying pattern to it. This is, also another kind of shout out to, to another sort of classic set of beats. This is a two-step. This is the fundamental drum beat in drum and bass. There's a million variations you can play with this. I put a couple of them in here, right? Right? It's kind of fun, right? It's just a bit of a goof, but it's kind of fun. But really, this is all sort of a precursor to the main event. And I think we all know what that is, the Omen Break. So I'm going to bring that up. And this shouldn't be any surprise to anyone, right? This looks exactly like everything that we've done before. I mean, I guess if you can see it. Let me move it up here. Right? It's a JSON file. It's got a channel. It's got a BPM. It's got some parts to it. And when we play it, let's see what happens. So right? Sound familiar? Now, there's two variations you might recall. The original Omen Break is 4 measures long. The first 2 measures are this straight beat, and then there's 2 variations on it. One where he drops the hi-hat, and the second where he drops the hi-hat and throws a cymbal in. Now, I have those programmed on here as fills, so we can play that through. So let's just start from here. We'll play 2 measures, then we'll play it in. There we go. We have it. So, in a scant 3 minutes ahead of schedule, amazing. In a scant 37 minutes, we have gone from being inspired by a funk song that's almost 50 years old, through showing off a production caliber, battle-hardened scheduling library, through like completely inexcusably retro drum machine, through to building our own version of the Omen Break and hopefully keeping that song alive for another at least 20 minutes. Anyway, as promised, okay, back over to the slides. Nope, not Ableton, slides. As promised, links to everything I've talked about, SkedX, the library, Beats the drum machine, and links to me and my Twitter. I have stickers, as promised, and I'm going to be around at the conference, obviously, for the rest of the day and the after party as well, so I would love to chat to anyone that would like to do likewise. Thanks for listening, everybody.